Okay, let's get started here. So this is the last regular day of class. We will talk a little bit about another subsection of the notes on testing mean vectors. This is not on the final exam, but I do want to just briefly mention it. We will spend some time talking about the final. And also, just as a reminder, to complete the regular course evaluation by Saturday at 1 p.m. When I was doing some last prepping for today's class, I noticed there were 7 of 9 students who have done it. So if you're one of the 2 who have not, please make sure to do it. Are there any questions before we begin? Okay. So testing mean vectors. So this is a classic topic for a multivariate course. A number of years ago, when I was doing another revision of this course, I ended up, instead of making that as one of the early topics of the course, as you will often see in multivariate courses, I decided to actually move it towards the end. And if I didn't get to it, that was okay. So it was like, well, depending upon how fast we go, if we end up having some extra time, we can talk about it. And the reason being is because I wanted to add some other topics to the course. And, if you're going to add topics, you have to take stuff out. And so of all the topics that I had been discussing at that time, I thought this was maybe the least important. So that's why I had removed it. But even though I would say it's the least important, it's still an interesting topic because it gives you a direct extension to something that you're all familiar with. And that is, your very first stat course, you learn about a hypothesis test for one mean. So let's say, you have some mean mu, we'll call it that. Is it equal to some constant? That's what mu0 means. So let's say maybe I want to do a hypothesis test for, what's the population mean for all GPAs here on campus? Maybe I want to hypothesize that mu is equal to 3.0. So mu0 will be 3.0. Okay? And so this is often the very, very first hypothesis test you ever learn about. And we have the regular old t-test statistic that's used to actually do the hypothesis test, where x bar is the sample mean, s is the sample standard deviation, and n is the sample size. And as you know, that if the null hypothesis is true, if we think of this t here as an actual random variable, we know that it has a t distribution associated with it, with n-1 degrees of freedom. And so what we look for in this hypothesis test is, do you actually observe a value of t that is unusual relative to a t distribution? So again, if the null hypothesis is true, if I draw out a t distribution, of course it's centered at 0, it's symmetric. If I have a test statistic that falls way out here on that t distribution, then that tells you, okay, there's very little probability of being out that far, so therefore it's unusual, and you would say reject HO. Okay, that's how we do hypothesis tests. Now, in a multivariate class, then, you learn about this hypothesis test. The only difference is I have bolded the mu's, meaning that now these are vectors. So perhaps this bold mu is equal to maybe mu1, mu2, and mu3. So, related to that GPA example, you could imagine a setting for students here at UNL. Maybe you were looking at 3 different characteristics of the students, and you wanted to test, is that equal to some constants? So in addition to GPA, or you could break up GPA by your major, a GPA by your non-major courses, and maybe some other characteristic. Okay. Now, how do we go about doing this hypothesis test? Well, we have what's called Hotelling's t-square statistic. It's a very classic way to go about doing this, and it's intuitive too. So this mu hat here represents basically the estimated mean vector. So in other words, the sample mean for your first variable over the sample mean for your second variable over the sample mean for your third variable. And we look at how far is it from the hypothesized mean vector. So it's a distance. And we take into account, though, the fact that these variables can be measured on different scales. They have different amounts of variability. So we have sigma hat, or estimated covariance matrix, in there. And so notice how this is very similar to some other distance measures that we've looked at. Here now we are looking at how far is the estimated mean from some constant mean vector. And if you were to look at the particular case where you have only one variable overall, meaning one overall mean, so p is equal to 1 in our normal notation of p is the number of variables, then this quantity here ends up simplifying down to your regular old t test statistic squared. So that's a nice property to have. Now, what about the probability distribution for t squared itself? Well, if we imagine we have a random sample from a population that can be characterized by a multivariate normal distribution, then if I take my t squared with some additional constants out in front, one could actually mathematically prove that that has a F distribution to it. And so, with the previous case where we only had one variable, we look at, well, do I have an unusual t test statistic value relative to a t distribution? Now we look at, do I have an unusual value of this t squared with some constants out in front? Do I have an unusual value for that relative to an F distribution? With p numerator degrees of freedom and n minus p denominator degrees of freedom. This ends up being a right-tailed test only, meaning that, and you can think of this in an intuitive standpoint, excuse me, essentially by having this mu hat minus mu 0 there, a transpose of it, and the mu hat minus mu 0 there, we're essentially doing the kind of the equivalent of a square. And so only large square different distances will end up having large test statistic values indicating evidence against the null hypothesis, and though that's why it's a right-tailed test relative to the F distribution. If that's confusing, you can think of the particular case of where p is equal to 1. Think about what a squared t test statistic value would give you, that only large values can indicate evidence against the null hypothesis. So we can look at a really simple example here. Suppose, and this is, I'm just going to simply simulate some data. Suppose we have a bivariate normal population. Mean is equal to 15 for the first variable, 20 for the second variable. Here's my covariance matrix here. So notice we do have some dependence amongst the variables. And, since I'm not going to test you over this, I'm going to really more briefly go over the code here. The basic thing that you need to understand is that I'm going to use the MVT norm package to help me simulate my data, similar to what we've done before. And I'm going to simulate a sample size of 20. If I page down a little bit here, you can see a graph or a scatter plot of the data. That's what's in red. And we have x1 on the x-axis, x2 on the y-axis for our two different variables from the bivariate normal. And the actual true mean for this population is what's denoted by this blue X there. And also I've put in there the contours of the corresponding multivariate normal distribution using methods that we talked about earlier in the course. And what the actual observed mean vector is what's denoted by the plus sign. And so we can see that they're relatively close to one another. And so just based upon that, do you think you're going to reject HO if I test is mu equal to this true mean? Or would I say don't reject HO? Well, you're probably going to say don't reject HO. So an example like this, it helps give you some intuitive feel for what will actually occur. Okay, so what one would need to do then is find mu hat, find sigma hat, and unfortunately there's not a particular function in the I guess the default installation of R that will actually do the calculations to calculate t squared. So I simply just programmed it into R, put the little set of constants out in front of t squared, and there's my test statistic. Test statistic is 1.08. I can go to my F distribution, which you will learn about in Stat 801, and get a critical value of 3.55 if my alpha value for my type 1 error rate was set to be 0.05. So since 1.08 is less than 3.55, I would say don't reject HO. And also I could find a corresponding p-value of 0.36, which is large. Okay, so that's how you can do it. So some other stuff that I have in the notes regarding this Hoteling's t-square is I said, okay, well, how about we simulate 20 different samples from the same population, and I'm always going to do a test of, is HO equal to this true mean vector that I know? And guess what? 19 out of 20 times I don't reject HO. One time I reject HO. And this is actually what you expect to have happen. Because if alpha is 0.05, that means you have a type 1 error rate of 5%. 5% times 20 is 1. Okay? And you can see then the corresponding scatter plots. Okay, so often of what's interesting is not necessarily to test is mu equal to one constant vector, but rather form a linear combination of your mu's inside your mu vector and then do a corresponding test of that. So here's something that you would see in an ANOVA section of Stat 801, but now approached in a different way than using analysis of variance. So let's say I have p equal 3. I might be interested in is the mean for variable 1, subtracting off the mean from variable 2, is that equal to 0? Meaning, is mu 1 equal to mu 2? Also, I could look at mu 1 minus mu 3. Is that equal to 0? Now notice if both are equal to 0, what does that say about mu 2, mu 3? Well, they would have to be equal to 0 as well. In terms of mu 2, mu 2 minus mu 3. And so, in an ANOVA setting, what would you typically call this? If, let's say, 1 represents your first treatment, 2 was your second treatment, 3 was your third treatment, what would you typically call looking at these the subtractions like this and setting them equal to 0? Does anyone remember? Excuse me? Yeah, we're doing pairwise comparisons. And so this is now just a different way to do this. And so now that we obviously are doing this we have a matrix algebra background, what this means is that one could take this matrix here, we're going to call this H, and multiply it by that mean vector. And that's where you get these comparisons. People often will also refer to these as contrasts. So if you do the matrix algebra, you get mu 1 minus mu 2 and mu 1 minus mu 3. Here's my H matrix. And so what this means then, in terms of if I want to do a hypothesis test, is that this is what my hypothesis test now looks like. This H matrix times mu is equal to some constant vector. How about we just call it little h, for lack of a better letter? And that constant vector is a 0, 0 vector. And, you could do this for any other h's. I'm just showing you one particular h here. And so in a general setting where we don't necessarily know beforehand what h we want to use, then we have a very similar test statistic to that Hoteling's t-squared. This is the extension of Hoteling's t-squared. And you can see very similar components to what we had just seen before, but now we have these h's in there instead. So another extension of Hoteling's t-squared to a situation that you're familiar with is that, in your very first stat course, typically the second hypothesis test that you ever see is something that looks like this. Suppose you have two populations, And you want to test, is the mean for population 1 equal to the mean for population number 2? And you looked at 2 different scenarios, independent samples from the different populations or dependent samples from the different populations. Well, we can extend this to a multivariate setting. So now I have bolded mu's there. And we can have a test statistic that has some similarities to what we just saw for Hotelling's t-squared. We can compare this observed test statistic value to something from the F distribution to make a judgment about these hypotheses. So this is for independent samples. If you had dependent samples, or what sometimes people will call paired samples, then what you could do, and this is basically exactly the same as what you would see in a Stat 801 course, is that now you adjust your data so that for the item that's in population 1 that's paired with the item from population 2, you take their 2, let's say, x vectors of data, and you subtract them. And now you're left with a d vector, and now you can use regular old Hotelling's t-squared on that d vector, or with the d's, you could say. And lastly, what I want to talk about is that, in a Stat 801-like course, you talk about analysis of variance, where you have, let's say, m different treatments, and you want to compare the treatment means. Mu1 equal to mu2 is equal to all the way to mu-m. And as you might expect from what we've been just talking about for the last 5 minutes, you can make all these mu's vectors. And to do that, instead of to perform a hypothesis test with the mean vectors, instead of doing analysis of variance, you have what's called multivariate analysis of variance, or MANOVA. And there are a number of different ways to form a test statistic, to do this hypothesis test, and so on. And this is what then the remainder of the notes talk about. Okay, so a real brief introduction to testing mean vectors. Like I said, I think the other stuff that we've done in this course is more important, more widely used, but this doesn't mean that this isn't of interest. Are there any questions? Okay. So let's talk about grades for the course. I go by what's obviously stated on the syllabus. What I've done, as you may have noticed over the last week or so, is I've posted all of your grades for the semester to Canvas. Please take a look at those grades just to make sure I didn't record anything incorrectly. It can happen that I accidentally record something incorrectly, so please double check them. And something that I also added last night was what is essentially your current grade in this class. And there's a field on Canvas called grade before final. And the way that I find that is I take what's in the syllabus, where your test 1 grade is worth 5% of your grade, test 2 is 20%, test 3 is 20%, and then your overall projects and quizzes part of your grade is 30%. Where that projects and quizzes part of your grade is number of points earned over the number of points possible. In total, that represents that we've had 75% of the grades so far in our course recorded. And so if I take this divided by 0.75, I get then your current grade. So for example, if let's say that you had 90.2% of the projects and quizzes, 95 on test 1, 80, test 2, 90 on test 3, if you put all these numbers into this equation there, that means your current grade before the final is 87.74, B+. Okay? And so, one could just simply go through R, or put all this stuff in R to do the calculation. Now, if you remember way back early in the semester in the week number 2 quiz, I asked you a question about calculating grades. and have you actually do a sample grade calculation. I recommend that you review that if needed, just to see how final grades are actually calculated in this course. Now, unfortunately, in Canvas, I don't have total control about what is actually being displayed. Canvas also gives fields called assignments, imported assignments, and total. Just ignore those fields. Those are not correct. I don't have a way to take them out, or if you know how to do it, let me know. I'd be very grateful. But they give you some information where they don't necessarily take into account, how grades are factored in this course. And so please ignore those. In the end, what do I actually use to do the grade calculations is that I simply have an Excel spreadsheet where I have everyone's grade in there. That's what I use to do the grades. Now, after finals are graded, what I will do is I will post your final exam grade, your overall percentage grade for this course, and also the corresponding letter grade. I will post that to Canvas. I will post also then an announcement on the discussion board saying, hey, this information is available. Okay. Any questions about grades? Okay, so let's talk about the final exam. So as we talked about the very, very first day of the course, it is a comprehensive final. It includes this multinomial regression stuff that we just finished last time. But to make it a little bit easier, it's not going to include any direct questions from the test number 1 material. And the reason being is because I feel as though that is more like meant to be background material to do what we want to do, like PCA or logistic regression. We need to do some other stuff first before we get to really the multivariate part of the course. There was some exceptions, like a multivariate normal distribution, that introduction, but there's not a whole lot. So there is no test number 1 material on the test. The test has at least one question from the remaining subsections of the notes. So there's at least one question from principal component analysis, at least one question from factor analysis, and so on. So please don't take a subsection, let's say, off in terms of your study. And as you see here highlighted in blue, there is actually a small format change for this test to make it easier for you. And that is essentially, I will do all the R calculations for you that are needed for the test. So on the test, you'll see some code and output listed there. And essentially, corresponding to a problem, let's say if I ask you, state the logistic regression model, you need to know where to look in the output to find the appropriate things so that you can state the model. So I think that this will make the test easier for you. You do not need to use a computer at all on the test. It's all going to be a paper copy. I've used this testing format a number of times in my courses at the end of the semester, because obviously I've had an opportunity now to assess your ability to use R on a test already, and I think generally speaking, students have liked that, and so that's why I do this often in classes. So again, I have done all the R parts for you in terms of the programming and getting the output. I will actually include comments in the code to help you out to make sure that you understand what this code is doing. There still needs to be some basic understanding by you about understanding how R operates. Like you have to understand, what does the print comp function give me? Well, it gives you the results that you need from principal component analysis. So there's still some R background that you need to understand from this for this test, but obviously it's not at the same level as you've had for the previous tests. So there's no computer use by you during the test. You will not need a calculator either. The way that I'm able to do that is as follows. Let's say I ask you to compute the principal component score for observation number 1, for the first principal component. For test 2, I would actually expect you to do that via R and show me your work. Instead, what I will say, compute it, but only just set up the equation. So, you might have to, say, okay, well, you write out 0.8 times x1 plus, 0.6 times x2 plus, whatever the other variables are. And where do you get this? Well, I maybe give you some print comp output, and you can find what those loadings, those coefficients are for this equation. And then you would say, okay, for x1, I plug in, whatever that observation number 1 value is for x1. Also for observation number 2, I plug in what the x2 value is. So you're setting up the equation. To some respect, it's a little bit like if you remember that Mahalanobis distance problem on test number 3, where you had to set up the equation. And yes, there was some stuff you needed to do in R, like find the mean vector, find the estimated covariance matrix. But imagine if that information was given to you, the mean vector, estimated covariance matrix, and now you just have to set up the equation. There is still a formulas and functions PDF that I've put together. It's essentially exactly the same as what I've done in the past. I've just added some multinomial, although I think I accidentally included the multinomial stuff for test number 3. I will get a printed copy of that and give it to you during the exam in case there's something there that you need to see. This test, though, is still closed book, closed note, closed video. I will hand out the test at 7:30 a.m. and you have till 9:30 a.m. to complete it. Okay, are there any questions about the format of this test?
Is there any sample question?
Basically, test 2 and test 3. Those will be sample questions. Imagine doing the same problems on test 2 and test 3, but I've given you the code in the output. Okay.
Is there such a question that you have the different output and you have to choose which one is the output for your question?
Yeah, I have written tests like that in the past where I'll give you a whole bunch of, here's one output, here's one output, and here's one output. You have to figure out which is the correct one. This test, I don't have that. Maybe I should have done that. But I do know, I pretty much finalized the test yesterday, and that should not, there is not that there. Okay. Other questions? Okay. Still on this kind of a test, you need to obviously show your work. Tell me, don't just give me, give me some explanation of, what you're doing. And I don't know why I still had that there. When I was editing it, that that shouldn't have been there. And the reason why to show your work is so that you give me, so I can assign you partial credit if needed. If you ever, encounter a problem where you don't know necessarily how to do it, that's where you need to give me some information about, I know that, you say something, I know you give me this, you give me that. I think I need to do something like this, but I just can't do it. Well, if you're on the right track with what you're telling me there, you're going to get some partial credit. In terms of the problem types on this test, similar to what we had before. There's going to be some calculations, but I've done some of that already for you. And as I gave you kind of an example of, well, state a logistic regression model. Well, look in the output, get the corresponding, let's say, beta hats, and be able to write out the model properly. Make sure you use the correct notation. Like don't, like if you're using the estimated logistic regression model, you need to put a pi hat there rather than just a pi. There is one short answer problem with parts that are not necessarily connected, similar to what you've seen on other tests. Also, to help you out, there is at least one problem, like number 1A and number 1C from test number 3. Remember, that was a particular problem where I had you do nearest neighbor classification with 4 observations, and you had to essentially kind of do it, let's say, by hand without the help of R. There's going to be at least one problem like that. So that was 1A, the nearest neighbor classification, and then 1C was the cluster analysis using the furthest neighbor method. There is approximately 15 points from the multinomial regression part of the course. Okay. Now, in terms of a review of the material, in terms of the test 2, test 3 material, I would basically just say exactly the same thing that I did before. So I don't have anything prepared for that here. You're, of course, welcome to answer or ask questions. But I strongly recommend that you go back to the videos of me doing those test 2, test 3 reviews and look at those again, because that will show you what I think is important, and that will hopefully then guide your studying for the test. Now, in terms of the material since test number 3, we just simply had this multinomial regression. So, please make sure that you can actually estimate and state a model. So what does that mean? Well, obviously I would use multinom to estimate the model. You're going to need to look at the proper places on that output to get the regression, estimated regression parameters so that you can state your model. One common mistake that I've had in the past for some students is that if you remember in the output for multinom, when I do a summary of it, there's both the estimated, let's say, beta hats and also the standard errors. And unfortunately, I've had students take the standard errors and use those when they're writing up what the estimated model is. And they think the standard errors are the beta hats. It's a small mistake, but unfortunately, I've had that happen more than once. Also, how do you find, let's say, pi 1, pi 2, pi 3? I could ask you a question on the test about could you actually derive what pi 1 would be, what pi 2 would be, what pi 3 would be. And while we haven't spent a whole lot of time on derivations in this class, I think that this is a very important thing here, because when you look at the actual model itself, it's not necessarily clear. How does this pi 1 come about? How does this pi 2 come about? How does this equation come about? And it's such an important, for what we are using multinomial regression for, in terms of trying to decide which group a particular observation comes from. Since that's such an important concept, I could ask you then to actually derive what pi 1 would be, what pi 2 would be. Then, of course, then how do you estimate pi? So pi 1, so, perhaps, I think on the formula sheet itself, you actually will see the equations for pi 1, pi 2, and pi 3. And I would say, okay, show me how you would find pi hat 1. Show me how you would find pi hat 2. Then what would you do next to figure out, should I predict group 1, group 2, group 3 for this particular observation? Then, in order to figure out or to gauge the accuracy of these prediction methods, you could use resubstitution. We know there are problems with that at times. You could use cross-validation. I could ask you a question on the test about, okay, suppose that this is my multinomial regression model. How would you do cross-validation with it to figure out what the accuracy of this prediction method is? Write out some steps to do it. So that will be a potential question. And then similar to what we've seen elsewhere, graphical methods to view the accuracy. Perhaps I could ask you to tell me what would be a way to graphically examine the accuracy of this method so that we know where this particular model is having problems differentiating between, let's say, group 1 and group 2, and where is it having successes. There's a number of different ways to do that. And it basically uses the same concepts that we did with like logist regression, nearest neighbor classification, discriminant analysis. Okay. So that's all I had to say about the final exam. Any questions? Any questions about any of the material? Anything you'd like me to go over again? Okay. Well, what's next in our class? Of course, I'll have office hours. And again, the final exam is Thursday. So 1 week from today, make sure you set your alarms for a little bit earlier than normal. The test is at 7:30 a.m. I think there should be rules about having to take a test when it's still basically dark outside. But I don't control how the scheduling is done here at the university. Obviously, all of you have been at other universities before. I've always felt that the way that Nebraska schedules these final exams is kind of weird. Other universities that I've been at, typically what they'll do is, okay, so if you have a Tuesday, Thursday class and it meets at 8:30, either your final exam is going to be Tuesday at 8:30 or Thursday at 8:30. It's going to be one of the two. There's, as long as, let's say then, the 10 o'clock classes, after an 8:30 class, for those 10 o'clock classes, if they will be on a Tuesday or Thursday at 10 o'clock as well. And so if you had a 8:30 final on Tuesday, then the 10 o'clock class final will be on Thursday at 10. I don't know why, because then there's also a weird thing where at least one common time slot for classes during the semester, let's say maybe you have, let's say, a Monday class like at 1 o'clock. And this probably isn't it, but for one time period, they will purposely change that to be like, let's say at night, like at 6 p.m. For finals here at this university. And I've actually had a case where that happened for a class I was teaching, and the doors to my building were locked. And so students can get in the building to take the final. Somehow they ended up contacting me, so I was able to let them in. I was kind of suspicious about what's going on. Why aren't there any students here? That's, I guess, all that I have to say. Thank you very much for taking this course. I hope that you feel as though that you've got a lot out of this course. I know, at least for me, I've enjoyed teaching this course. I hadn't taught this course for a few years, and I'm really glad that I was assigned to teach this course again because I really like the material. In fact, I kind of, after teaching this course again, it's like, I kind of like to write a book on it. I was actually asked by a colleague to co-write a book on this about 3 years ago. And at that time, I said, I'm just starting to write the second edition of my categorical data analysis book, so I can't do that, but I would like to. And also I said at the time, well, I don't know if I'll be assigned to teach the course again. And now after teaching this course again, I'm thinking about it. Okay, well, good luck with your studying. If in the next week you have any questions, of course, please feel free to post something to the discussion board. Okay, that's all.